we are the gesture-based Slam team. Although our name is just gesture-based, we added a lot of new stuff. My name is Jayam, and my partner is Bhavna. So we'll give you a summary of our whole experiments and everything, all about the analysis and whatever we did throughout the project, along with the videos. So our problem statement was to explode the navigation and mapping methods. So the first thing that we wanted to do was to use Mayo, the EMG band, for navigation and mapping, so that it's like a EMG band which records the muscle movements and have navigation through it with the human operator giving the signals and map the environment with it. That was like a guided mapping, you can say, guided slam. The next was to make a random obstacle avoiding robot which would follow an algorithm which is completely random, take random turns, go in different directions, keeping on avoiding obstacles, like we did in our first assignment. The next one is 2D camera visual slam, in which we are using the camera data to generate maps. So basically, it feature recognition and see whether it has come on this like whether it has explored this particular region where it is right now. And in the last part, we mixed all the details, like the obstacle avoidance, the camera data, and the odometry data in one, which goes around in the environment. Makes sure that it is tracking all the features, and if it has like already explored that region, so that it would see that the features are matching, and it can like realize that the odometry is also recognizable, so it would go to a different location and start mapping again. So the first thing, like I said, was Mayo. So Mayo has EMG sensors. So if you see in the inner side, there are metal plates. So this one plate is an EMG pad. So there are such 8 pads, and each pad is connected to different muscles on the hand, and they would give their own values, based on which we can know whether you are forming a fist, you are showing left, right, forward, like something like that. The main issue that the challenge was the Thalmic Labs, basically, who invented this and whose product it is. They don't give support for Linux systems, and ROS, as we know, that the best works on Ubuntu. So we had to make drivers, and we did not have anyone to talk to, but we managed to get drivers and convert them to ROS packages. The next issue that we had was, previously we were working on Ubuntu 12.04, and as we shifted to 14.04, there were again compatibility issues, like we all developers have. And sometimes what happens is the raw data is quite ambiguous, which creates a lot of issues and has a confusion, which I'll explain in the next slide. And like sometimes, as it is connected by Bluetooth, it has connection lags and limited range. And if you make random hand movements which are not recognizable, it might lose connection and reset. So that was one of the issue. So these are all the hand movements that we are using. The top 4 ones are the one we are using. This is right, this is forming a fist, which is go forward, stretch is stop, and left, this is left. So now if you see, this fist and this fist is quite different. The thumb is inside in this case it's outside. So these two are also giving some ambiguous data. So but we choose this one, as in, if you make a fist, your muscles are stretched more. Even in this one, instead of having the whole hand, if you try doing two fingers, it is also kind of a stretch. But in this, the data was more clear, hence we used the whole stretch. Now this is the whole ROS interface. This is the interpreter node, and this is the Mayo node. So Mayo node gives the Bluetooth and the connection, and interpreter interprets the Bluetooth. So basically, the given action to like this actions, all the given signals to all the actions, and publishes twist message respectively. Now linear X is for translation motion, and angular Z is basically for your rotation. So like it can be controlled accordingly. And linear X, we made it such way that we don't have to give fist forms every time. it increments every time a fist is given. So basically it's every time a forward is given, and it goes back to 0 when you have a stop signal. So it increments so that you don't have to keep on, you are increasing the speed using your forming fist. Now let's take a look at the video. So this is the mapping it's doing. This is giving the actions, and this is the actual video that we recorded with it. There might be some lag because we had to mix two videos, and I have the EMG band on my hand. The video is not real time, like it's real time, but we had increased the speed by 2x, so it was this fast. Like you see, it is more realistic when we did it. So if you see here, the dark violet region, the purple, yeah, it's purple. The purple region is the near obstacle, so that it would make sure it doesn't strike through, like go across them. Like right now, can you see if it got stuck? This was the connection issue. We lost the camera, and like we had to, like we started the video again. This is left, right, forming fist, and you can see it's happening. And this was the whole map formed. This is the hallway in Atwater Kent building in WPI. Oops. Okay, so the next part is obstacle avoidance. So in obstacle avoidance, what we did was we are getting a camera data, right? So it is basically in one plane, it is getting all the depths using the infrared sensor on the Kinect. We divided, so if you see here, it's kind of this range is of 60 degrees plus minus 30 from the center. So we divided the whole range to 3 sectors, sector 1, 2 and 3. So depending on each sector, we count the number of points that are crossing through the threshold value, and we count those points, and based on those points, like let's say this was 210 values, 210 values and 220 values. So if out of 210, it's whichever has the largest values, depending on that it takes a turn. And the main issue that we faced was of nan. Like nan is not a number, which is it means. So you get a nan when it's either too close or it's too far. So what we did was we still made the robot move ahead, like when it's nan, and check on its odometry if we are taking odometry data or camera data, depending on that, and check whether the frame and the position stays the same. If it does, it takes a round and explores if he's getting a different value and goes into the different value, different direction. So this is the video of a normal obstacle avoiding with random motion, and it was giving a slam along with it. So the first is the slam. It's giving random motions. As you see, it came here near, it would change direction, and it changed according to the values it's getting from the depth sensor data. Now this was a hallway, and there was a place, like a place between it, so it could go to a different hall. So we wanted to go straight, but as it was random, it took it a right turn and went inside. So get the volume's too high. So if you see here, you might see that there are too many obstacles over here. So this was the point where it's like got slow, real slow, and here it got stuck with the students' bags, and we had to reset it. We had to pick it up, and we are placing it here. And now we'll compare this with the real time. This is the real time that was going on, and if you see, it's quite accurate. The scan data is pretty good. Sometimes it behaves crazily, and it might just take random turns, like out of the blue, if there is an interference and seeing something else which is it is not supposed to. This is the map it's creating while it's moving. Okay, so this was the obstacle avoidance. Now let's go to the next part. We created a simulation so that we can troubleshoot. We don't have to work on physical environment every time. And this was the simulator, and it helped because in the end our Kinect broke, the drivers broke, and there was some issue, we could not fix it today. So we are recording it in the simulated environment. The map also gives the odometry data, and based on it, it can retract and go to another location. Now Bhavna will explain the remaining part.
Hello everyone. After we were done with the odometry slam which we had, we started with the 2D camera slam. So what we are doing is I am outlining in terms of the algorithm here. We are first taking 2D images from Kinect as input. So it's give us a stream of 2D images which we are recording at the frequency of 10 Hertz. On these images we are running the ORB filter, which basically gives us the features between the two consecutive frames. With those features we are finding the homography, and choosing this homography we can find the relative x and y, which we use in making the odometry for that. And also we are saving these features, so that we can bookkeep these features and we can compare with them if we run into the same frame and basically the same area again. So using these things we are making the map using the x and y values, and these features we are using to detect the previously visited scenes. So this is one snapshot how it is comparing. Left side are the current frames and right side are the previous frames, and for each consecutive frames this algorithm, it compares the points and it saves the features. For computational A's we are just saving only 10 best match points and not more than that, and even we have a threshold in comparing so that we don't compare the false positives. So we'll see one demo of this SLAM. So this is how it is as it is running. This window is gazebo window, which shows our whole world. In this window we are seeing the frames as they move consecutively, and also this area, it tells us which is the, this is based on basically it's just telling us which area is safe, as it's saying. So on basis of these two things we are, one second. On basis of these two things we are checking. Right now we don't see anything here because the frames are not matched, because it's traversing everything for the first time. As we go ahead in this video we'll see, once it rotates again through the same area, it's actually able to find the frames. And at the back end what it is doing, it's saving the relative x and y, and soon we'll see how the trajectory is created using those things. So, and in this case you will see that it gets confused over some corners. It's just due to the noisy data, because gazebo also behave very realistically. So we'll just move forward. Okay, so just after this, so we see that as it is, let me just move back. So as it is moving through the same domain again, which has already visited, we say that it's telling us the frames are detected as they were previously. So we'll just stop there. Yeah, so this is the map created. It's the same area, the area it's going through, but it is very erroneous, because which is actually obviously true. If we see that the camera images, it might have jerk as well. It transpose everything into x and y domain. It doesn't have any depth. So this is the error that we are facing in this case. And also if we see this map created through using this method, it can just give us the trail that the Turtlebot followed, and we can just imagine that there was some obstacle here, that's why it might have moved the other way, but we can't get the actual depth data or the boundaries of the corridor or something that we are traversing. So to solve that, we actually move forward to sensor fusion and using both data to create a more robust SLAM. That's when we came to the sensor fusion using Kalman filter. We had both data, odometry data and camera data. In odometry data, what problem we have is it is too much jerky, so we don't have stationary values all the time. In camera data, the problem that we have is it is only giving us the trail, it's not giving us the boundaries. So we are combining the depth data with the camera data and using them both to create this SLAM algorithm. So I'll just go through quickly how we filtered this data. So this we see, red is the odometry data, which you see is very jerky, as I mentioned earlier. So green is the camera data. In camera data you see that we have sudden jerks in this case. So these are basically due to, this is due to the hardware problem in Turtlebot. Turtlebot works discretely. So when you give a command, it executes that command of motion and then it gives a jerk to stop. It's not very smooth. So this is when it happens like this. So frames get flipped, but since we don't have any depth, everything is captured into x-axis, which makes it very much erroneous. So we used Kalman filter to predict these values, and we use the odometry data as our data and camera values are as our updates. But also we set the weights, such as weights we basically decided based on the experiments that how it is settling better. So combining these two in this way, we created this output on the basis of which we will be generating the trajectory finally. Same we see in the case of y-axis. If we see here, the data is very noisy if we use only on the base of odometry. However, in camera data we are having the drifts, but if we combine them both, we are getting pretty accurate data. In case of depth data, we basically don't have any data from camera as it is 2D, but our odometry is very jerky because of the discrete motion of the turtlebot, as I mentioned. But using Kalman, we are basically filtering it, and the final trajectory is smooth. The motion is not smooth, but the trajectory and the map that we are creating, it works better. So we'll go through the demo of this part. So in this case, if we see, this is our consecutive image frames. This is our odometry data, which is comparing the depth. This is our gazebo frame. So initially when it just starts, as the word is so small, it gets confused if it has seen that frame earlier or not. However, excuse me for a second. However, if as the bookkeeping grows, it actually is able to maintain the frame. So initially we had some random frames matching in this window. In this window, however, now it's not, because it's now it's correct and it has not traversed this area before, so there is nothing. Later on, when we visit this area again, we'll be seeing the frame matching in this window. And in this window, if you see, it's recording the depth data, and it's making decision over that. So it's keeping track of what is the clear range in right direction, left direction, and front direction, and on the basis of that and our obstacle divider code, it's taking decision which direction to pursue. So how we have designed this is basically following the boundaries. So if you see, it's going towards the boundaries and it's walking along them, so that we can have a better map. We had some multiple algorithms that we tested over it, and this is one we found the best. So it just checks that and moves like that. I'll just move forward, and now it's here. So if you see there, now it's crossing that corridor again, and we see here that it's saying that match is detected. This information we use to correct the SLAM if we have more errors, and this can be used to correct it. Yeah. And now we come to the future scope. How and why these algorithms can be used. We haven't used any algorithm which is automatically made, rather we tried to build things from the scratch. And potentially these can be used in the case of shared autonomy, where we give target to the robot to reach somewhere, and at the same time, say it finds some dynamic obstacle. So what robot can do using this code, it can take over the control and intelligently avoid this obstacle, and after avoiding this obstacle, it can give back the control to the user and execute the desired action. Second possible application of this is it's basically in the terms of navigation. If we have HTML mode, so this is something which is very much used these days. So you can log in through the web page, and then you can provide a target position, and the robot can basically autonomously move to that position, and you can have it there. So these are some cool applications of our project that we have done. We really had so much fun using this, and we welcome your suggestions and questions. Thank you.